Hello, everyone. My name is Faraz. I'm one of the main organizers at TMLS. Thank you so much for attending this workshop. Just a quick message that you would have received an email last night from Hopin. That's actually your actual link to the conference that is starting tomorrow. Once again, all the workshops / content is being recorded and will be shared after the summit. So please look for an email. We'll obviously send you a couple of reminders before we also send out all the videos as well too. So thank you and enjoy your workshop.
Okay. So hello, everyone. My name is Trambitas. I'm a solution lead at Jon Snow Labs, which is an AI company specialized in natural language processing techniques for the healthcare domains. So in today's presentation, I will walk you through some of the processes and best practices that currently guide our activity when working on NER projects. Usually those have very high demands in terms of accuracy, volume of the processed documents, and speed of the processing. So in this context, choosing the right annotation team and a good process and an adapted tool for data annotation and then for predictions validation are crucial steps for ensuring a high quality of your training data. So let's discuss each one of those three elements in more detail. So first of all, when working on NER training problems, NER model training problems, you need high accuracy data set. And for doing that, for building that, you will need an annotation team. So this should be composed of high experience domain experts because they will have to work on the documents, they have to understand the particularities of the domain, the subtleties of the data that they will have to annotate. This is the first very important requirement. And after that, your annotation team should have annotation experience, and they should be very careful about the requirements of completeness, consistencies, the structure of the annotations, and so on. For instance, the completeness is one of the most important requirements, and annotation team has to make sure that they annotate all the occurrences of a given concept, for instance. Then they have to ensure consistency of the annotations. For that, usually you have to create annotation guidelines and make sure that the entire annotation team aligns to those guidelines. Then what we have noticed in our previous project is the fact that the short annotations are most relevant and thus the labeled data should be limited to one or two or a minimum number of adjacent words if possible. We should then avoid overlapping labels and so on. So the bottom line is that the annotation team has to have domain expertise, have to understand very well the documents and the content of those documents, and then they have to understand how the results of their work, so the annotations that they will create, will be used in the project. So for the projects we are working on at Jon Snow Labs, we are using a team of, we have created a team of domain experts in the healthcare area, which is composed of around 8% medical doctors, 10% pharmacists, and 10% nurses. So those people are very familiar with the documents that we are analyzing because they are generating them on a daily basis, they are analyzing them, and they are very familiar with those documents. They understand them in great depth. Then you need a very clear process which will allow you to eliminate all the errors and to have a very concrete steps to follow and iterations. So this process is illustrated in the following schema. So first of all, the first step is to define the taxonomy. So this taxonomy consists of actually a list of labels and a list of relations which will be interesting in our documents and that we want to predict and we want to annotate in the document, right? So once we have this list of relevant entities, we will just define annotation guidelines for each one of them based on the team experience and also based on preliminary analysis of the corpus of documents that we want to work on. So once we have this first version of the annotation guidelines, we start the annotation process, right? So all the annotators start working on the documents and annotating all the labels that are in the taxonomy and also marking down all the relations which are relevant. Okay, so after that, after this individual annotation step, we have a validation step. So there are two options here. Either the annotator will cross-check each other, or we can establish a validator, someone who is more senior in the team with higher experience in both the annotation process and then on the particular domain of the documents, which will cross-read the documents and then check whether or not the annotations are correct and whether or not they are consistent. So after this step, we will set up annotation disagreement meetings where all the annotators in the team participate together with the data scientists who are working on that project. And they all discuss very concrete examples of encountered labels and how they were managed by the annotation team, how they were annotated in the corpus, treated. So if necessary, those disagreement meetings will, at the end of those meetings, we will have updated guidelines. Okay, so if some edge cases were encountered during the last iteration, we will discuss them, and if necessary, we will add new rules in the guidelines or update the existing rules to cover all those new encounter situations. Okay, so then after the disagreement meeting, we will update the guidelines and then we will reiterate. So start the another sprint when the annotators will work individually on the new documents. There is also the possibility that when the guidelines are updated, annotators will have to revisit the already annotated documents in order to correct them so that they will reflect the current guidelines. Then we will also have the validation step, which will cover around 20–30% of all documents which were annotated in this iteration. And this will continue throughout the project. So what is very important here is to set up the weekly disagreement meetings and to have data scientists who will actually exploit those annotations, participate in those meetings and give feedback, and they give very useful inputs to the annotation team on how to manage certain edge cases or certain particular situations. So this is an example of taxonomy. So in the taxonomy, we have a list of entities or labels that are of interest for the documents that we are currently analyzing and processing. And then we have a list of relations. So the relations are between two different entities or labels. And we have some special types of relations such as negation, uncertainty, and also modifiers who are special attributes which can be linked to entities. So at this point, at the definition of the taxonomy, we just have to come up with a list of entities of interest together with the customer, of course, and then choose whether or not we support all those relations and maybe specify the cases where we want to extract them or not. So the next step will be to define the guidelines. So for that we have to study a sample of the documents and then write the guidelines for each label and for each relations. So I'm showing you here an example of such guidelines which were created for a project focused on cancer diagnosis. For instance, we have the the label cancer diagnosis and the location and all sorts of other labels of interest. But in this case, we are just walking through a couple of examples on how to label cancer-related data sentences. So the main point here was that we were focusing on one cancer word and one anatomical reference. But in order to, for instance, this is a very simple case where we have, she has breast cancer, we annotate the entire chunk, breast cancer, then we have a couple of words between the cancer word and then the location, the anatomical reference. We decided to select the whole chunk and annotate it as a cancer diagnosis. For instance, in this example, we have ductal breast cancer. So breast cancer will be extracted as a cancer diagnosis, while ductal will be considered as location. Same in the previous sentence. Then we have some more special cases where the cancer is implied. For instance, here, she has metastatic disease with right breast primary. Breast primary implies the fact that there is, this is the source of the cancer. So it will be extracted as an instance of the cancer diagnosis. While metastatic disease will be extracted as a metastasis. Okay, so another relevant example here is her mother had ovarian cancer. So this is still a reference for the label of interest, in this case, cancer diagnosis. So we will extract it no matter the fact that this refers not to the current patient, but to a relative or some close family member. So this is related to the completeness of the annotations and the fact that we have to label all the occurrences of a given label all over the document. So no matter to which person this particular label refers to. Okay. Another example is here. The biopsy for was positive for DCIC, which is an acronym for ductal carcinoma in situ. So both occurrences of this should be highlighted and should be labeled, both the acronym and a carcinoma in situ, which is a cancer diagnosis, while the ductal still refers to the location. So so it's a very good practice to go into this much detail with very clear and concrete examples and be very specific regarding the words and the characters that should be included in the labeling process. Okay, another very important thing is to treat this process as an iterative process, and we have settled on weekly iterations. As I told you before, first we have annotations which are created by the annotation team. Then they are reviewed and validated by senior annotators, and we have disagreement meetings to sort out the disagreement and to refine the guidelines, and then go back to the previously annotated documents and correct them if necessary. So what is very important in this annotation process is to ensure the agreement across the annotation team. Okay, so they have to annotate in the exact same manner and be very consistent across the document from the beginning until the end, because usually the annotators get tired if they are dealing with longer documents, and while they're extracting everything at the beginning of the document, sometimes towards the end of the document, they miss some of the labels. Okay, so it's very important to keep consistent, and because the model that will be built both based on those annotation cannot be more accurate than the duration of the annotator agreement. So this is a highly important element. Now there is another problem, the fact that the annotation process it's a very complex process, error prone because it's done manually, and we have to find ways of speeding up the annotation process. In order to be able to process as many documents as possible in a short time with a short team of people, and yeah, in order to obtain a relevant corpus of training data for the model training. Now, in order to achieve this requirement of high speed, we have two approaches. First of all, at the beginning of the annotation process, what we are doing is comparing the taxonomy that we want to extract for the current project with what we already have in terms of pre-trained models. So we look at our library of pre-trained models and we compare the labels that they are predicting with the labels that we currently need for the new project. We choose one or several relevant models for that, okay, from our library of models, and we apply them to predict some of the annotations. Okay, so once we have the taxonomy, we have a list of relevant models. We apply those models on the list of documents that we want to annotate in order to predict something. And this way, the annotators will not start from scratch, but they will have at least some of the labels predicted in the documents that they annotate. So this is one step, one possibility to speed up the annotation process. And another way of doing it is through active learning. So the active learning process is will actually take the data which is annotated by the annotators, and they will use those new annotations, those new examples, in order to refine the pre-trained models or to build new models which will be later on used in order to create predictions for the rest of the documents which were not seen so far. Okay, so those are two very important steps that we are currently supporting with Spark NLP. So the pre-train, so using the pre-trained models in order to predict annotations at the beginning of the project, and then keep improving those models and creating new ones if necessary in order to help the annotators process the documents quicker and work less. Okay, so we have the team, the process. Now what we need is a tool that will allow the annotators to quickly go through the corpus of documents and then create the annotations, and then eliminate as much as possible the human error and try to ensure consistency. So there is a long list of tools which is currently available on the market. We have used several of those over the years, but finally we decided to build our own tool because neither one of the tools that we used so far was respecting all of the key requirements that we think are absolutely necessary for an annotation tool. So first of all, the annotation tool should ensure a high productivity. The tool should keep the annotators in the zone, right? So they should not have to navigate between different windows, so they have to have all functionalities on the annotation screen, okay? This tool should be intuitive and easy to learn because the majority of the annotators are domain experts, but they are not very tech savvy. So they have to get used to the tool very quick and then be able to use it in a very short period, okay, quickly. Then the tool should offer support for keyboard shortcuts because it is much easier to work with the keyboard for creating annotations and navigating between documents and between the created labels than with the mouse, okay? Then really it should be a very fast, it should allow a very fast annotation because when you are processing thousands of documents per month, you start counting the clicks and the eye movements and the distance between different buttons and so on. Another important element is for the tool to allow the automatic transition between documents locking the documents which are already in process by another user so that we avoid working on the same document twice. Okay, so another very important aspect is the support for team working. Okay, so we have to be able to create projects and teams and then assign different users to the team based on their roles and so on. Then we have to be able to customize the workflow according to the project needs and according to the actual problem that we want to solve in that particular project. Okay, so we have to be able to tag documents and retrieve them by status and by user and so on. Okay, another very important thing is the audit trail and the versioning of the annotations and also of the models that we are using for predicting labels. And then also support for active learning is very crucial because this will speed up the annotation process and it will ensure high accuracy of the results. Now, we have, as I told you before, we have created our own annotation tool, starting from an open source solution provided by Label Studio, and we have customized it to suit our needs. We are currently offering this annotation tool for free to all Spark NLP enterprise users. So everyone who is interested can apply for a trial and start using this. So this is the workflow that we are currently supporting for the annotation tool. So we are starting from a health record, right, who is usually can be a text document or a PDF document or scan image or something of the kind, which can be imported into the annotation tool by first analyzing it using the Spark OCR library. If necessary, we can also use the de-identification package for removing the personal information which is contained by the document. Then we feed all the result to the Spark NLP for healthcare pipeline, which will run the pre-trained models if necessary, if those exist, and then it will load the documents together with the predictions into the annotation tool. The healthcare experts, which are the annotation team members, will then access the documents and the prediction via the annotator, and then they will start annotating or correcting the current predictions or annotating from scratch new documents, which will then be used, be fed as training data into the Spark NLP for healthcare module, and then we will start iterating over this. So I have added here a couple of screenshots from the annotator tool. As I told you, everyone who is interested in trying this out, we can provide the trials. Okay, so this is the main screen where we set up the project. So the project can have a name, a sampling type. This is very relevant when trying to eliminate bias from the annotation process. So there are two options here, uniform or random. Yeah, then we can add a description to the project so that we can later on retrieve it, and the guidelines. Okay, so here we can define the guidelines that will be used by the annotation team. Those can be consulted from the labeling screen by anyone. Okay, so once the project is created, we can add the team members or the annotators, and we can refine their permissions. Usually when we are working on closed environments, processing personal information documents, we have requirements to cancel the export permissions or yeah, we usually fine-tune those according to the needs of the annotation team. Okay. So after you create the project and you add documents, you can then start the labeling process. So this is the main screen for the labeling. In the upper side of the screen, you can see the taxonomy, so all the labels which are of interest, and then by simply selecting, pressing the key which is assigned to each one of the labels, and then selecting the text of the text that you want to label, the label will be automatically added to the list of extracted labels. Okay, so the labels will be colored differently according to the entity that they are linked to, and you have here a short, so an indication of the label which is assigned to this particular chunk of text. Okay. So once the user, so the annotation process is extremely simple. You just press the key corresponding to the label and you select the text, and this is automatically added to the list of results. For adding relations, for instance, here we have a relation. You just click on the on one of the elements which are involved, one of the labels which are involved on that relation. Press the arrow key and then click on the second one. So it's very easy to add relations. Once the users finish with this document, they just click on the submit button. The current completion will be saved. We have a full audit trail on who added what annotation, at what time, and who created which completion. And after you click on the submit button, the next document will be displayed. For consistency, for ensuring the consistency between different annotators, we have possibility to compare completions for the same document, for instance, and this is also very useful to check the accuracy of the predictions, because on one hand we can have the data or the document annotated by a human user, and on the other side you have the data which is annotated by a pre-trained model, and then you can visually have very relevant clues about the rate of error. So this is of course an easier process for data validation, and also this is very useful when training new annotators who are joining your team on how the annotations should be done, because you can just compare completions created by different annotators. Okay, so here you can see how the predictions look like. So in the right side of the screen, you see that there is a difference between completions and predictions. The completions are created manually by human users. The predictions are created by models. You can, by clicking on this button, you can create a new completion based on those predictions. So predictions are not editable, so you can just see them. But if you create a completion based on those predictions, then you will be able to correct the predicted data. Okay. Then we have the list of tasks. So this is the tasks screen with all the imported documents. The ones which are green are completed, and the ones which are on red are incompleted. So we have different filtering and search functionalities in order to be able to retrieve very quickly the documents which are of interest. And we have the possibility to attach different tags to the documents. For instance, once a validator will go through the documents which have been annotated in the last week, and he finds some problems with some of the annotations, he can tag that task as needing corrections, or just validate it and say everything is okay. Okay, so once we have data, once we create the annotations and we validate them, we can export them. either in JSON format or in CoNLL format. And both those formats are very easy to exploit, and they can be fed directly into the Spark NLP framework for model training. So this is everything I have for this presentation, and I will give the floor now to Veysel, who will continue from this point on, and he will explain how to actually use those annotations for model training.
Hello everyone, thank you, Dia. It was a great intro to what we do here and what we are going to do for the next 1 hour, I think. So right now I'm a lead data scientist at Johnson Alves working with Dia, and we are solving these problems every day. So we are training these models every day. So I hope you all see my screen. So I'm just moving forward, okay? So let's start with what Spark NLP is. We released our first releases like October 2017. We are sitting on the shoulders of Spark. Our main goal was to be able to provide a single unified solution for all NLP needs that could be scalable. So there was no Spark NLP library at that time. So we built this team, and then we are 100% virtual team, by the way. Based in the United States, Johnson Labs, but all the team members are around the globe right now. So we have an active delivery cycle, like every 2 weeks we release a new version, and we try to cover every NLP task that the other libraries are already covering. And this is the goal is to be able to have production ready library, like implementing the latest state of the art papers into runnable code. So we have 3 modules, libraries, like public version on the right hand side. On the left hand side, you see the licensed version, which is the clinical one. And the third one is Spark OCR, which you are not seeing here right now. So let's just focus more on, I assume that you already know the what Spark NLP is. I'm just going to focus more on the left hand side and then train some models. Like this is not a hands-on session, but I will try to cover as much technical detail as possible. If you ask some questions during the, I'm not able to see the questions right now, which I was seeing while Dia was talking, so I was trying to reply. Maybe at the end of the session, I can cover all the questions, or the moderator would just intervene and ask some questions. So in Spark NLP clinical models, we have 4 main components, which we call clinical entity recognition, to extract some entities out of, like, this is the main topic of today's talk, by the way. And the clinical entity linking, everything starts with NER in clinical NLP problems. So, and then we use that knowledge to build some other downstream tasks, like clinical entity linking, assigning some SNOMED code or RxNorm code, or assigning some assertion status, like if that problem entity is already there or absent in terms of negativity scope. The other one is the identification, like to hide the sensitive information. So let's move forward. So Spark NLP have 4 different, like, supported in 4 main languages: Python, Java, Scala, and R. And the syntax are very similar, so you can jump from one language to another using like quite similar syntax. And then state of the art means that best performing academic peer-reviewed results, so that we try to compare our results with the papers published, like papers with .com or nlpprogress.com. We try to compare ourselves, but we want to have in production, not just on the paper. Introducing Spark NLP, we have many blog posts and workshops about Spark NLP, which you might have seen before. When you Google Spark NLP and Johnson Labs, you will see tons of blog posts about that, which I'm one of the writers. Spark NLP is like a building blocks. So you add a block that you would need to accomplish some certain tasks. So on this one, Like you feed a text column, and then you get a sentences, and then you tokenize the sentences, and then you clean that text, that tokens, like normalize, and then you can get the word embeddings of each normalized token. Or you can add some spell checkers here, or you can just do some text matcher to extract just the certain tokens, etc. And then you build the pipeline, and then you can save that pipeline or transform over any other data frame. So to the bottom, today we are just going to focus more on healthcare NER models. They are already mentioned in detail how we build our NER models. But let's see, let's talk a little bit about what we do with these NER models in healthcare at first. So on the left-hand side, on this chart, you see that there is like everyone is sitting, every company is sitting on piles of data, and in healthcare, it's hard to process that data due to its NLP is already a hard domain, like it's an ultra domain specific area that everyone needs to build their own model. And in healthcare, it's even harder. So even like a basic English is also hard, but healthcare NLP is the hardest part of this NLP world actually. So the goal is to be able to utilize this data, like string data, through machine learning algorithms, and then use this insight to decision-making processes. That's where NLP comes into play. So assume that we have this clinical node, and then we want to be able to highlight them, not highlight. We are not just doing this for highlighting. We need to be able to use these entities to build some other works as a downstream task, right? So which means that we need to be able to extract them as a clinician does. So we ask, our annotators, these guys like healthcare experts are the physicians, are the doctors, medical doctors that we hire, that we contract to data. So when we have a project working with a client, so customers, so we hire some people, or we use our own onboard physicians to annotate. Some of the guys ask a question, this annotation has any rules or not. It all depends on the problem that we are trying to solve. If the problem is to be able to detect some metastatic, the pattern, if a patient will develop a metastasis on certain sites, we at first gather, like whole team members gather, and then decide which entities to annotate. What kind of entities would help us to accomplish that goal at the end. So that's why we take the records to Spark OCR. If it's already TXT, we skip the Spark OCR part. If there is some sensitive information, we apply the identification so that our developers are not able to see the sensitive data, or if it's allowed to see out of NDA agreements, we can just skip the step as well. And then we start to annotate all these texts. Like the healthcare experts are in touch with the data scientists every day to build this NER model. Otherwise, they might just drift through somewhere else that would be useless in terms of the model, so that we also have them understand what basic deep learning models work, how every single word is important. We try to explain them so that they would try to think like a model, or because we are trying to imitate that human decision, right? So the goal is to be able to highlight these entities as a physician does. That's why we try to have them in a close cooperation, so that I talk to my annotators every day, so that if they have some mistakes, I realize that inside the model by checking the metrics, and then we go back or do some other NL conversions. So in healthcare, usually like there are some data, and then there are some judgments that needs to be that needs to be made based on these data. So one human can do this like as many like a few times in a given time. So the goal is to be able to automate this process using some smart algorithms that could help, that could but that could automate some process as a physician does. Instead of annotating one single document per hour, it can annotate 1,000 documents per second. So that's the goal. That's why every annotation and every NER model is case specific. So let's start with clinical NER, as we just have, I think, 45 minutes. So everything starts with NER in clinical NLP, which means that everything, this is the smallest, like this is the lowest meaningful step in every clinical NLP problem, because we start building the pipelines from on top of clinical NER, because NER extract the meaningful chunks, and then we use these meaningful chunks for the other tasks. For example, that posology NER, like a medication NER, give me 40 units as a dosage entity, and then I use that for the dosage and then get the Aristotle code, for example. Or if there's a drug name here, I get the Aristotle code for that. And then if this is a, like there's a sickness mentioned as a, like a detected as an entity, I get the SUNOMED or ICD-10 code for the normalization purposes, for like a reimbursement for the insurance companies. And then I try to find, if I want to find, if I want the invites on patients to clinical trials, I want to find the best patients that would suitable for my goal. So I want to know that the problems mentioned in that patient's records are still relevant. So I check its assertion steps, if it's present, absent, or might be related to family. Or we just want to share our data with some other authorities, but we want to cover some, conceal some information, sensitive information according to HIPAA rules, so we use the identification. So all starts from clinical NER. So that is the admiralship of clinical NER models. Okay. And let's talk about a sort of like a small problem, not the small, but how we frame our annotation and model building steps. So we start with the problem at first. At every time we start with the problem. We just we don't just highlight this for fun. We need these entities for the other steps. So the goal, we assume that the goal is predicting if a patient would develop a metastasis on certain site or not. A patient would have thousands of documents for the last 10 years due to her visits, her clinical visits, like radiology reports, clinician, patient, email, conversation, etc. So the goal is to be able to automate this process, to extract some knowledge, and then to see, because the doctor, the physician, when he checks a report, he uses his previous understanding of that patient, of the previous records. So he is just using some common experience. So our goal is to be able to imitate that process. If a human can do this, a model can do this as well. Of course, we are trying to make this as close as possible, but we are still not there, of course. So we take the health records, we extract the entities, we get the assertion status, like if it's absent, present, family related, and then we apply some feature engineering steps. Like, because there might be many other indicators that would help me to detect if this patient would develop a metastasis or not. And then using some NLP techniques, train a model, and then like a classifier, etc. So that's the step. So that's why we need NER at the core of this problem. This is the output of NER. In Spark NLP, we have around more than 20 pre-trained NER models already. So you can just plug and play. And I just put like 4 of them here. On the left-hand side, you see the problem treatment test. These are all trained on clinical benchmark data sets. Like this is coming from 2010 I2B2 data set, problem, which is supposed to extract problem, treatment, and test entities. On the right-hand side, you see a 2018 posology NER, like medication data set that we trained our model and then enriched with OpenFDA, like a drug data set. And then anatomy NER is another challenge. Like we train this model inside Spark NLP using our own embeddings and algorithms, like some customized algorithms, and then try to compare our benchmarks with them. And then when we, if we need posology NER inside our pipeline, I put this one inside my pipeline. And then if I also need anatomy NER, I also put this one and then connect the dots inside my pipeline. Like the output of anatomy NER and posology NER will lead to assertion status model, for example, so that I could get the negativity concept of each point. So we did a little bit conversion. I am already, for the last 1 week, I'm planning to do the large scale one right now. We are going to publish soon about our results. So I just compared one single result. This is the one that is coming out of my education NER, and this is the Amazon Medical Component. So as you can see, we are doing a little bit better compared to what AWS does. And like we can also extract this with meals, and we have some metrics. So I'm going to share the metrics later on with the public as well. So we are at par with AWS Medical Component, sometimes even better. So since I've been talking about we are trying to beat the benchmarks, we try to implement the state-of-the-art NER algorithm, which I'm going to cover in a few minutes, and then implement inside Spark NLP so that you can scale this training process, like not the training, but the prediction inference step, on multiple clusters. So we have our own embeddings. We also use Glow, BERT, Elmo, Albert, XLNet, etc., which I'm going to cover as well. Right now, the state of the art is, according to nlpprogress.com, let me go back, according to like 93.5 is the state of the art, and we are 93.3 for 2003 CoNNL. This is the public one, by the way, using our library. So, and it's not on the paper, it's in production right now. So how do we develop our model? We took this paper from 2015, Nichols paper, because in NER, there are multiple approaches, as you may know. It all starts with the classical approach, like the rule-based, because when you create some enough features between entities in a sentence, you can understand its role without even training a model. That was the classical approach, but it's just a limited version. And then ML approaches, like treating this problem as a classification problem. Every token would be classified, every chunk would be classified into different classes, and deep learning approaches. What we use is, we use BiLSTM CNN architecture, charge CNN architecture, and implemented inside Spark NLP through TensorFlow. So we build a graph in TensorFlow, and then train and fit inside Scala, and then wrap inside Spark NLP. So how this algorithm works? I say that like charge CNN, BiLSTM, not the CRF. We have also CRF version, but I'm going to focus more on the softmax version right now, which, as you can see at the final prediction layer, classification layer, we use softmax. So everything starts with every sentence. We take a sentence as a training, and then each row, at first we take the sentence into, this is the first feature, token by token. This is the token feature. Token features are embedded, like getting vectorized through embeddings. We are using clinical embeddings. We have our own PubMed clinical embeddings, 200 dimension. Or we can still use BioBird, which already is supported by Spark NLP, or BioVec, or Google 100D Glow embeddings. It doesn't matter. So anything inside Spark NLP, any embeddings you can use to vectorize your word to build a model. Of course, if it's clinical, the word coverage will be higher, and the accuracy, the relationship between the tokens will be well represented while training the model. And the second feature is casing feature. Casing feature is because if it's a uppercase word, it might be like abbreviation or people name or some city name. So it's an important indicator for an NER models, like the title case, lowercase, numeric, uppercase, etc. So we, for each word we get the casing features as well. And we skip the third one. We don't implement it in the original paper. There is a part of speech feature as well, which we don't use. But according to our tests, our benchmarks, like show part of speech didn't make it better, so we removed. And the last one is char features. Like the character features are useful for if you have a typo, And if there are some typos between inside a word and it's omitted or converted through OCR instead of I, converted to 1, etc. So we should still be able to understand the type of the entity as a human. So if you, instead of just taking the word tokens, if you take character by character and then treat this problem like a CNN, like convolutional neural network, like taking 1D and then 3 is right, like I'm going to show right now, which means that you can just get the pattern between the words. So if like I can say that it's like a tree chart, follow the tree chart pattern, etc. So, and then, for example, we get the character embeddings through CNN, like one by one, and then we feed into the convolutional layers, and then extract the features. And as a second one, like the word embeddings, we already have it. And the casing features, we concat all of them and then feed into the BiLSTM architecture. And then at the end, there's a softmax layer. So this is how the CNN process works. Character-based CNN works. So this is the upper left side of the architecture. So we have a layer for the characters. Assume that we have this one, health. It's 6 char. So we have like 3 1D convolutional network, so that it would just sliding window each character by character, and then we would have an embedding at the end, like a char-wise embedding. So it needs to be fixed size. So because the graph needs to be defined before starting the process. In Spark NLP, when you start the process, it will show you, it will say that use this type of graph that I'm going to mention as well. So because it needs to allocate some memory to train that much light. So this is our word during the training. This is our sentence. We get the token features, we get the casing features, we get the character embeddings, and then there are labels. These are the ground truths. So our goal is to be able to model will at each epoch, it will try to pass through the network and then try to get a try to predict something and then compare itself like a regular deep learning parameters, and then calculate the loss and then back propagate and try to reduce the loss. That's the goal. So this is a token-based multi-classification problem. So every token can only have one label at all. So at the end, this is a ground truth. Assume this is a ground truth, and this is the prediction. So this is for this one, it's perfect match. This is match. There's a problem here, which means that it didn't. So there will be some loss here. There will be some cost, and then it will be implemented. It will be try to reduce. And as you can see, the goal is to be able to minimize this error, and then the rest of the process is a classical machine learning problems, like trying to reduce the loss, optimize the problems, and then get the highest F1 class-wise score. So the source of the training starts with CoNNL dataset. We use CoNNL 2003 format in Spark NLP. In 2003 CoNNL format, we use bioschema. Bio means that like John J. Smith. This is a person name. So we let the model know that this is the starting of person entity. So we say like B per, B, sorry, this column. B per, like the beginning of this entity. I, not the beginning, but in the middle, like inter, like any other than the first one. And the O means nothing. So John J. Smith is a 4-gram chunk, right? So the model will try to find the relationship between what makes this first token as B, not the I. So that's why we try to add some granularity to the model. We can also use this one in Spark NLP, but we are not using. I don't suggest, because there should be some difference between first and second token in practice. Like John Smith, B per, I per, New York, B log, I log. So Dia just explained how we do this. When on an annotation tool, when a physician, when an annotator clicks something, it will just highlight that entity. And then we have our own converter in Spark NLP, which is just taking this JSON file from annotation tool, create this CONNL file. So that no human involved by conversion. We already have Spark NLP annotator for that. So that they just click, they just annotate, and then developer just use another annotator to convert the export the JSON file to a CONNL file and then run into Spark NLP DL annotator. So we take the data, CONNL data. We have CONNL reader converting into Spark data frame. We can use any other on embeddings like a 100, 300, 786, 500, etc. Any embeddings in Spark NLP you can use to vectorize your words, your word features, and then NER DL approach. This is the heart of the model. This is the char CNN LSTM architecture lives in. According to NLPprogress.com, the state of the art is 93.5. I think I covered this slide before, but it's repetitive. So we right now 93.3 on the test set, and the state of the art is 93.5, which means that we are at top 3 and by only production ready library right now. So which means, and the most beautiful side of this algorithm is this architecture is that you don't need to play with the architecture. You can just tune the parameters. You just need to feed your data. Even if, like we are supporting 22 languages right now, we don't change our algorithms to train new models for another language. If you want to support Turkish language, we take a Turkish data set and Turkish word embeddings. Or GLOWs are multilingual, of course. GLOW 6 billion word embeddings is multilingual, so you can use that one as well. And then you don't need to write any single deep learning code to train a model because the architecture will not be changed. Of course, there will be some languages that the accuracy might be lower, but according to our implementations for the 22 languages, we are getting really nice scores just by changing the embedding vectors and tuning the models. No need to write a new TensorFlow code. And these are the pre-trained NER models that we have inside Spark NLP right now. All of them are dedicated to extract certain entities. So if you want to extract some drug-related entities, you will use posology model. If you want to extract some sensitive information, you can use other multiple options. If you want to extract just age, you can use that one. If you want to extract some smoking, like risk factors, or obesity, you can use this one. These are licensed, by the way. So there's you need to be licensed to be able to use these pre-trained models. We are about 20 right now, more than 20 different. You can just connect the dots, like throw all of the models inside the same pipeline and then use whatever you need. Instead of trying to decide which one to use, you can just feed in all of them and then try to extract whatever you can get out of your data. The goal is to be able to highlight as many stuff as possible for that clinical node so that could be useful for the rest of the process. We are still training some of them. We are going to add new models soon. These are all the benchmark data that are being used by NLP researchers in medical domain. So we are also using the same and then try to beat the benchmarks. Like these are some test results that I'm trying to cover for the last few months. And this is the code. So this is the code is that simple. So assume that we have CONNL file here. This is the CONNL. And then I just read it with CONNL reader. I decided to use BERT embeddings. You can use word embeddings as well. There is an article explaining all this, by the way. There is a webinar and article. So when you, on Medium, you can go this one, like write this one, and then just write named entity recognition Spark NLP, Google this, and then you will find this article, this blog post. And there will be, you will see a link to the workshop as well, like similar to this workshop. And this word embeddings will get the word features, like embedding features, and then this is the algorithm that I'm talking about. It will use the sentence token and bird features, like bird is coming from, like bird embedding is coming from this module, token is coming from CoNNL reader, because CoNNL reader creates tokens as well, according to the like a CoNNL file. And then we have the ground truth label, and this is the predicted column. So you can train like 100 people, but usually 10 people would be enough for me. Right now, for example, we can train a state-of-the-art clinical models in 1 hour for 12 or 10 people. In 1 hour, just as long as you have enough data. And then you can fit and then save this model and then use anywhere you want. So let's see how we do this. I'm not going to write a code, but I'm going to show that you can write how you can write. We have a public repo, Spark NLP workshop, tutorials. Under tutorials, certification trainings, you will see a directory. And then we have public and healthcare versions. Since we are talking about healthcare in here, for the healthcare notebooks, you will see Databricks version as well. And some case studies like clinical text classification, how you can use Spark NLP to solve clinical text classification problems. And I covered every clinical models in Spark NLP in that repo. So you can just go and then open in Colab. So let's, I already opened one of them in Colab. This is the first one, which is, let's go back, let me show you. Certification trainings, healthcare, and then I just click this one. And then I set that open with Colab. Right click and open a new tab. So this one is opened. So which if you have a license, you can run this. But if you don't have a license, you can still use NER, because NER is free, by the way, NER model. So you can use your own model or Glow embeddings. You will see not that much difference depending on your uniqueness of your data set. You can still use the public word embeddings, and NERDL is in both sides. It's not just licensed. So NERDL can be used, as you can see. Let's go back here, public. You will see NERDL training here. So this is also the same model. You just change, so you don't need to install it. It's all in Colab. You just install some, like download some data set and then start your training. So let's talk about how we do this for clinical. So the pipeline, let me walk you through my decision process. So I start the Spark session at first, and then I think we have 20 more minutes, so I can cover in detail if I'm not fast. So when I started the session in Colab right now, I didn't need to install anything. The Colab, there is a setup cell here that I see for you. If you are using the public version, you will see in the other notebook that you will not need these. So you start the session. You can start the session manually. For example, if you have a large data, you may want to have large driver memory. Or you can define the jar that you want to use, like a previous version. Or if you want to increase the buffer size, serialize the buffer size. So the error messages will tell you, will guide you through if your memory is enough or not. Another important thing, on Colab, you can also use GPU for Spark NLP, because Spark NLP has the GPU version as well. You just, like, when you import Spark NLP, and then like a Spark NLP that start and GPU 2. When you do this, the GPU version will be loaded. Okay. And the session started right now. From now on, that the session will be guiding our process. So I imported some basic stuff, and then, for example, this is NERDL model, Spark NLP NERDL model. I wanted to load the pre-trained version. So NER posology is already there. I just showed you the list. There's a GitHub repo which is called Spark NLP models GitHub repo. You will see all the names over there. if you are confused which one to use. This is the notation, like the name of the trained model, language, and version. Like if this is public, it will be public models. And then I say that it will use the sentence token and embeddings from the previous annotators inside the same pipeline. Because NER-DL model, to make a prediction, right now it's going to make a prediction. To make a prediction, it will need all these features. So since I'm just going to quickly cover the prediction steps and then show you how you can train. So we start, assume that you wanted to get some predictions for the text in-house clinical text. And you have a data frame, like a column, one column of text. And we start building the pipeline. At first, we say that, okay, this is the entry point to Spark NLP. Everything needs to pass through this document assembler. We create a data frame, Spark data frame at first, and then feed it into this pipeline. And at first it says, okay, I'm going to see the text column, and then convert, and then create a document column in Spark NLP. And then from now on, the rest of the annotators will use that document output. Like sentence detector will use the document and create the sentences. Tokenizer will use the sentence and then create the tokens. Word embeddings will use sentence and token. Why sentence and token? Because it needs to know if it's a bird embeddings, it's context aware, so it needs to know which sentence it lives, that token lives in. And then we fit the output of word embeddings and token and sentence to NER model. So this is like a building block, as I said before, connecting the output of certain annotators to other models as an input. And then output will be NER label. NER converter is very useful tool here because we have I and tokens, like I person, B person. You need to have some meaningful, John Smith, like meaningful chunk. NER converter does this job for you. And then we build the pipeline, fit on an empty data frame. Because this is pre-trained model, you can just fit on an empty data frame. And then at the end, you will have a fitted model that you can get predictions. So let's just download PubMed sample from our public S3. I already downloaded. You can also run this one. This is public. And I say that read the CSV into Spark data frame. Now I have a Spark data frame. This is the PubMed sample data set, Spark data frame. And it has only one column, text column. Now I want to transform this over my pipeline. My pipeline is model, fitted model, which is here, like it's already fitted. So when I run this, it's going to produce, like out of one column, it will produce all these columns for you. Because document assembler created this column, sentence selector created this column, token assembler created this one, and NER created this one. NER chunk is converted the tokens into chunks. So right now I have one large data frame that I can just use whatever I need. Let's see what's inside. So it says, like, for example, token, each token, as I said, this is a multi-classification problem. Each token will get a label. This is the predicted label coming from NER-DL pathology model, sorry, clinical model, because in here, let's see what I used. I used NER clinical pre-trained model. This is another NER model, like problem, test, and treatment entities. So it will give me test, problem, or treatment entities as a prediction. As you see, like this one is detected as a test, as the first token. This one is as a treatment. This is the first, this is the second token, etc. So let's see how many of them are detected, are predicted. It says like 1,500 problem entities. You can just check the B versions because they will be joined by the I versions, I chunks, I tokens. So you can just say that, okay, I have around 800 problem entities, 700 test entities, and 600 treatment entities in total for 100 rows. And then you get the NER converter output, NER chunk, it says. You will get rid of I and B text, and then you will end up with this, like chunks and this one. So you can build this pipeline by yourself. So let's get something like basic Python stuff instead of Spark. If you want to do this with pandas, you can use Light Pipeline. Light Pipeline takes Spark NLP model, FITIL model, but reduced to overhead of Spark itself. So it's on single machine when you do this. And now you can just full annotate any text without creating data frame. So this is just text, any string like this one. So you can just full annotate or annotate. If you want to get the metadata, you can full annotate. And when you annotate your text, all the columns that you saw above will be provided as a dictionary. Okay, so like a Python dictionary. So, and then you can just look through. So NER, like this is the dictionary coming out of this one. And then I want to say that, okay, just look through the first part and then give me the NER chunk. And then I write some codes. And at the end, I can create my dictionary, list of dictionary to the pandas data frame. And then you can just convert this to the CSV, save as a CSV and send your colleague or write to any other database. Okay. This could be like an API for you. So at the end, you can write some HTML to highlight the codes as well. You can feed through. You can also see how we highlight this in this repo notebooks, which is very simple. This is just using the outputs coming from previous pipeline and then assigning some random colors. Okay, so if you want to change it to do NER posology, you just change the NER model, pre-trained model, and then replace that one here. This was clinical NER, right now it's posology NER. If you want to use multiple, you can just put multiple one, like we can just write clinical NER that is already downloaded above. But right now NER converted, this one only accept inputs from posology. So I need to add another NER converter and then say that use like, and then check, set or change its input and output columns. It's like taking the output of one annotator, use as an input to another annotator, so that you would build your large pipelines. Okay, so when you transform, like this is fitted on the empty data set. When you transform, you end up with this one again. And these are all the columns and metadata that is being created right now. So let's see the training process because we don't have time. Let me show you how we train model. Training. Okay. NCBI clinical disease data set. You can just run this cell. It's also free because it's coming from our workshop repo. This is a CoNNL file. I just read this with our CoNNL reader, and then I ended up with this one. That txt CoNNL file converted into data frame through CoNNL reader. And then I got some basic statistics, like how many entities do I have? I have 3,500 disease entities, like 300, actually 3,000 disease entities, just one single entity. This is a binary classification, looks like. It's disease or not. So let's see how many, let's just skip, and it's another representation. Okay, as an embeddings, I decided to use embeddings clinical, which is licensed. You can use any other embeddings here inside Spark NLP. You can check Spark NLP models GitHub repo to see the embeddings that we support. You can even use BERT or Elm or XLNet or Albert here, because it will just give the embeddings of the word that is given as an input. And let's see. Or if you have some Janssen or FastTask trained word embeddings, you can still use that, like word embeddings model dot, not the pre-trained, but load from your disk dot load, and then fit on a data frame, like empty data frame, and it will be word embeddings model again. And you will be able to use that inside Spark NLP. So it's that easy. And then this is the algorithm that I run. It says that take these features from the previous annotators This is my target that you need to compare yourself, and run 2 epo, use 64 epo, batch size. These are all parameters that you need to tune. And take the 20% of the training set as a validation. Give me some logs. Also include the confidence when getting inference, when getting predictions in production. And after each epo, use this as a test set, which means that validation set will be, you know, that validation set will be used to tune the parameters, tune the model weights, but the test set will not be touched, but as a convenient check for, as a developer, you would want to see how your model develops, like how your model gets optimized after each epoch, like the training and validation loss and test loss. So you may still want to see the test metrics after each epoch. That's why we have this one. So how did I create this one, by the way? I created like this. I have the test from the same data set. I can split, or I already have a test as another data set. I downloaded both of them, as you may remember. And then fit it, like get transformed on clinical embedding, so that it would be, so that it would add a word embeddings column as well, because Coronado Reader doesn't have word embeddings column. So, which means that in production, I'm creating every features that the NER DL model would need to get some predictions to compare itself. And then write to this, and then in the model, I point to the path to that model, that data set. So you can say that, okay, write my logs to that folder. If you don't specify, it will be annotated logs folder in your home folder. When we train this one, like, as you see, like just 2 epo, it's 1 minute on Colab right now. Just 2 epo, and sometimes like 5 to 6 epo is enough. And let's see the logs. Logs, you will see something like that as a log. At every epoch, you will get validation metrics and test metrics. Test metrics will be just there to show you that if your model is overfitting or you need to stop. Right now, we are not able to stop and then resume. No, you will just run like 15 epoch and then check your logs and then see, okay, I'm doing bad. Let's stop at 11 epoch or 12 epoch, and then go back and train again. The model is running, like the TensorFlow is shipped with Spark NLP when you install that. So it's using the TensorFlow 1.15 inside Spark NLP. When you fit the model, you can just save and then load into another pipeline. You remember this one? So we have been using pre-trained models here. Right now, I'm using my own model, and then using inside another pipeline. So I can just say that, okay, she has a metastatic breast cancer to the lung, and then use the light model, and I can get, okay, this is just a basic Python right now. Like metastatic is a disease entity, breast cancer is a disease entity, lung is a disease entity from this one. Just after 2 epo, like in 1 minute. Right now we have this one. So this is the article that I mentioned, blog post on Medium. There are more explanations here that you can read, understand other, like how NER model works. You can also check our workshop repo that I just mentioned. In the public version, these are all free. All of them are free actually. Just to load some pre-trained model, you would need license on the clinical version, but on the public version, you wouldn't even need that one as well. Like text classification, sentiment, and these are all free. We even have a clinical spell checker. We just included into our scenario. So let me check the questions. I can just check the questions. Where are the chats?
I think you have to stop sharing your screen.
Yeah, yes, I just found it. Okay, so I don't see any question, which is good.
There is a question on how to add more models in the same pipeline, but I think you covered that.
Yeah, let me share again. So this one, like writing a generic NER function, this part. So I wanted to use here, I wrote a simple function to simplify the process, I say that, okay, I can just call this, say that, okay, just give me, like this one, right? Use clinical embeddings, and as a model, NER clinical, and I would just call it, and then the pipeline will be, so this would be a generic pipeline that you can create. If you want to have multiple, like, let's go back to our postology NER. So if you want to add more than once, I think I already covered that one. You can just create another one here. Let's say clinical NER, like let's say postology NER and NER postology. And since this should be like output needs to be different, right? Because the sentence belongs to the other one. So like sentence and token will be same, embeddings will be same, input would be same, but the output should be different. So let's say NER postology. So that I can differentiate like the clinical output and the postology output. Now I also need one more NER converter because this is using the NER coming from clinical NER. Now I need to write something to use the NER postology as well. So I will use this one. Let's say NER post converter, rename it. And this would be, so NER chunk postology. So when I run this, I need to add this to my pipeline as well. So when I fit this, it will download both of them, and then will be fitted on empty. And when you run your text, when you transform your text, you will get two predictions from two different models. You will see NER chunk and NER chunk postology, like NER postology and NER columns. Like we see here, you like NER column, you will also see two more columns, NER postology and NER chunk postology columns. So training your model is as easy as, like, as I can show on this one. Create your CoNNL file and then run inside Spark NLP, NER DLP. We also have CRF approach, which is still using LSTM, but not using softmax, like changing the last layer. That's the only difference. You can just select which one to use. You can also check the assertion status and the identification models. Assertion status is very useful for classification purposes because the entities might be misleading by itself. So every entity needs to be joined by an assertion status to be used in other downstream tests like test classification or etc. Okay. Anything else? So let me share the GitHub links as well. If you guys still here, I can share the GitHub links. I think they are already, okay, they are already shared. So when you just Google Spark NLP or OS, you will see tons of links about that one. We have the webinar recordings as well. Diaz talk, my previous talks, we have ODSC talks, so you can find many of them. If you cannot, we are available on social media, so you can just reach us. And if you want to test, by the way, Johnson Labs offering free license nowadays due to COVID. So you can just apply, and we will just get back to you as soon as possible, and you will be able to use 30 days. They are 30 days, right?
I think now for the COVID projects, we offer 60 days licenses.
Okay.
And also for researchers and universities, those can be even longer. And for regular trials, we offer 30 days.
Perfect. Which means that, and Dia is the one behind all this stuff. So she will provide all this license and assign one of us, like me, to you guys, so that you can get fast, quick answers to your questions. You can connect me. You can connect with us through LinkedIn as well, and we will have many other webinars and talks and projects going on around the globe. Okay, thank you. Thank you for listening to us.
Yeah, thank you so much.
Thank you guys.
Okay, have a nice workshop. Bye-bye.
Yeah, so we can just, I'm just leaving, right?
Yeah, I think so.
Okay, thank you guys. Bye.
Bye-bye.